Hi, hello, and welcome to BK'sTechStack. I am BK. Today, we are going to learn about advanced generative AI, building LLM applications.
Hello everyone, and welcome to BK'sTechStack. I'm excited to guide you through building advanced applications with generative AI. Our focus today is on large language models, or LLMs, and how we can leverage them for sophisticated tasks. We'll be exploring the practical implementation of a technique called Retrieval-Augmented Generation, or RAG, which is key to enhancing LLM capabilities. Before we dive deep, let's set the stage. RAG, or Retrieval-Augmented Generation, is a powerful technique. It essentially allows LLMs to access and use external knowledge. We'll be using LangChain, a fantastic framework that makes building these RAG systems much more manageable. Think of LangChain as your toolkit for assembling these complex AI applications.
Let's quickly recap some fundamental concepts. Vector stores are vital. They store information in a way that's easy for AI to search through, which is essential for RAG. LangChain's retrievers help find the exact information needed. These pieces of information are then given to the RAG model to create accurate answers. Now, let's think about the impact. Imagine building a system that acts like an incredibly smart search engine, giving users instant, accurate answers. Traditional models can sometimes struggle with this, but RAG changes the game. It's about breaking down complex data and finding the most relevant bits. This makes systems faster, smarter, and much more effective. How could you use RAG to enhance user experiences?
By the end of this session, you'll be equipped with several key skills. You'll understand the shortcomings of older AI models and how RAG addresses them. You'll learn practical techniques like text splitting, using vector stores, and integrating different AI components to build effective question-answering systems. Let's first look at the challenges we face with traditional generative models. These models, like GPT-3, are trained on massive amounts of data. However, their knowledge is essentially frozen at the time of training. This can be a significant issue when information changes quickly, or when we need highly specific, up-to-date answers.
These limitations can manifest in several ways. We often see hallucinations, where the model confidently provides incorrect information. Accuracy can also be a problem. Responses might be based on old data or miss crucial details. And as mentioned, the knowledge is static. It doesn't learn or update in real time. This is where Retrieval-Augmented Generation, or RAG, comes in. RAG models smartly combine the power of generative AI with the ability to retrieve information from external sources. The result? Responses that are not only fluent, but also accurate and deeply contextualized, effectively overcoming the limitations of traditional models. The strengths of RAG are quite significant. Firstly, by retrieving relevant information, we can ground the model's responses, drastically reducing hallucinations. Secondly, accuracy is boosted because the model can access current and specific data. And thirdly, the knowledge can be dynamic, allowing the system to incorporate new information as it becomes available. Let's visualize the RAG process. It starts with a user's question. This question is used to create a retrieval query. This query searches an external knowledge base to find relevant information, or retrieved text. This retrieved text is then combined with the original question to form a full prompt. Finally, the LLM uses this comprehensive prompt to generate the most accurate response. So what exactly is Retrieval Augmentation Generation? RAG is a technique that brings together the best of both worlds, retrieval and generation. It's a framework that uses retrieval models, like those based on BERT, to find relevant information, and generative models, like GPT, to create human-like text. The core idea is to overcome the weaknesses of using either approach alone. Let's pause for a quick check. Thinking about traditional generative models, what do you consider their main challenge? Is it generating coherent text, factual accuracy, processing text, or integrating with vector stores? Take a moment to consider the limitations we just discussed. Now, let's break down the building blocks of a RAG system. To make RAG work, we need several interconnected components. Each part plays a specific role, from preparing the data to finding the right information and finally generating the answer. We'll go through each of these essential components step by step. Here's a visual overview of the main components. First, we have the text splitter, which breaks down large documents. Then, the embedding model converts text into numbers. These numbers are stored in vector stores for quick searching. The LLM itself generates the final answer, and utility functions help manage the process. Notice how they form a cycle, ensuring smooth data flow.
Let's start with the text splitter. Large language models have a limit on how much text they can process at once. This is called the context window. The text splitter's job is to take a large document and break it down into smaller, manageable pieces that fit within this window. This is crucial for preventing information loss. Next up is the embedding model. This component uses advanced deep learning techniques to convert our text chunks into numerical representations, called embeddings. Think of these embeddings as a way to capture the meaning of the text in a format that computers can understand and compare mathematically. This is key for finding similar pieces of information later on.
Following that, we have vector stores. These are specialized databases designed specifically to store and quickly search through the embeddings we created. They're like a highly optimized library for our AI's knowledge. Finally, the LLM takes the user's original question and the relevant information retrieved from the vector store to generate a coherent and accurate answer. Lastly, utility functions act as helpful tools in the RAG pipeline. These can include things like web scrapers to pull information from websites, or parser to read different file types like PDFs or CSVs. They essentially help us gather and prepare the data before it gets processed by the other components, making the whole process more robust.
Let's compare how a traditional LLM works versus a RAG pipeline. In a traditional setup, the user asks a question, the LLM generates a response directly. It's simple but limited. With RAG, the process is more involved. The query goes to a retriever, which consults a vector DB, our data source. It fetches relevant text, combines it with the query, and then the LLM generates the final response. This gives us much richer context. Here's another quick check to solidify your understanding. In the context of a RAG model, what is the primary function of the vector store? Is it storing and retrieving text representations, splitting text, generating responses, or evaluating accuracy? Think back to the components we just discussed.
All right, enough theory for now. Let's get practical and build a simple RAG model from scratch. We'll cover the essential steps: loading your data, preparing it into manageable pieces, creating numerical representations called embeddings, and setting up the system to retrieve relevant information. We'll be using the powerful LangChain library to make this process efficient and straightforward. The first step in building our RAG knowledge base is loading the data. LLMs, by default, don't know about specific, private, or very recent information, so we need to feed this information into our system. LangChain makes it easy to load data from various sources, like spreadsheets, text documents, and even PDFs.
Okay, let's begin with the code. First, we need to install the LangChain library if you haven't already. Then, we import all the necessary tools. Notice we're bringing in components for vector storage, loading documents, creating embeddings, splitting text, and interacting with language models like OpenAI's. We also import OpenAI and OS for potential API key management. Now for step 2. We need to get our data. In this example, we're using LangChain's web base loader to fetch content directly from a web page. I've provided a URL for an article about YOLO NAS. This command will download the content of that web page and load it into a document object, which will store in YOLO Loader.
Step 3 is crucial: splitting the data. As we discussed, LLMs have context limits. This code uses character text splitter to divide the loaded document into smaller pieces, or chunks. We define parameters like chunk size and chunk overlap to control how this splitting happens. Then we apply the splitter to our YOLO Loader data, storing the resulting chunks in YOLO NAS chunks. For step 4, we focus on embeddings and setting up our vector store. We're using OpenAI embeddings to create the numerical representations of our text chunks. To make this efficient, we're using cache-backed embeddings, which stores these embeddings locally using local file store. This means we won't have to recompute embeddings every time, saving time and API calls. Step 5 is where we build our knowledge base. We use the FAISS library to create a vector store. We feed it our YOLO NAS chunks and the embedder we just set up. This efficiently indexes all our data. Then we create a retriever object directly from this vector store. This retriever will be used later to find the most relevant information based on a query.
Moving to step 6, we establish the core retrieval system. We import chat prompt template to structure how we ask questions to the LLM. We define a function, format docs, to properly present the retrieved context. Then we create our prompt template, instructing the LLM on how to answer, and initialize the chat OpenAI model, which will generate our responses. In step 7, we chain everything together. This code defines how the retrieved context, our prompt template, and the LLM will interact. We create a RAG chain from docs that takes the context, formats it, applies the prompt, and gets the LLM's output. Then, RAG chain with source sets up a parallel process. One path retrieves context using our retriever, and the other passes the user's question directly. These are combined to create the final answer. Finally, step 8, retrieving the response. Here, we take our configured RAG system, RAG chain with source, and invoke it with a specific question about YOLO NAS. The system will perform the retrieval and generation steps we've set up. We then print the content of the answer field from the response. Let's see what it says.
We've successfully built a RAG model, but our work isn't done yet. In a real-world application, it's vital to know how well our model is performing. This means we need to evaluate its responses for accuracy and relevance, and then continuously monitor it to ensure it maintains high quality over time. Let's look at how we can do that.
Model evaluation is typically done using a set of test questions and their known correct answers. We can use a tool like LLMchain to systematically compare the answers generated by our RAG model against these ground truth answers. This process involves setting up an evaluation chain, having the model generate predictions for our test questions, and then comparing those predictions to the actual correct answers to calculate an accuracy score.
Once your RAG application is live, ongoing monitoring is essential. Keeping the quality high can be challenging. Fortunately, RAG systems provide components that help us monitor performance in production. This allows us to gain valuable insights, ensuring that the model continues to provide accurate and relevant responses as time goes on. Let's look at some specific methods for monitoring. The Simple Model Monitor class is designed for this purpose. A core function is log interaction. Every time the model is used, this function logs crucial details, exactly when the interaction happened, the timestamp, what query was asked, and how long it took to get the response. This data is fundamental for analysis.
Beyond just logging, we can visualize and calculate key metrics. The plot execution times function helps us see trends in how long responses take over time, giving us a visual sense of performance. And get average execution time provides a simple, clear metric, the average time it takes for our model to respond across all logged interactions. These tools help us quickly identify potential issues. So where is RAG used in the real world? It's incredibly versatile. Think about customer support chatbots. RAG makes them much more helpful by providing accurate, context-aware answers. Search engines can use RAG to understand queries better and deliver more informative snippets. It's also powerful for content generation, helping create things like news articles or detailed product descriptions. We've covered a lot of ground. Now for a practical demonstration, implementing RAG from scratch. This demo will guide you through integrating retrieval and generation. You'll learn to split documents, create embeddings, index them using FAISS, and use a custom prompt. The result? Concise, context-aware answers powered by an LLM. For a hands-on experience, please refer to the Jupyter notebook mentioned. One last quick check before we wrap up. What is the main goal of monitoring and evaluating a RAG-based model? Is it about reducing costs, ensuring sustained accuracy and relevance, text splitting, or document retrieval? Think about why we need to keep an eye on our AI systems after they're built. Let's summarize the key takeaways from our session. We learned that traditional models have limitations, and RAG addresses these by integrating components like retrievers and vector stores. RAG significantly boosts performance using tools such as text splitters and embedding models. LangChain is a powerful ally, simplifying the creation of these advanced RAG systems. Ultimately, RAG pipelines are essential for efficient and accurate question answering in real-world scenarios. We've reached the end of our presentation. Now it's time for the most important part, your questions. Please feel free to ask anything about RAG, LangChain, or building LLM applications. I'm here to help clarify any doubts and discuss how these concepts can be applied to your specific projects.
Congratulations! You just learned presentation topic. Now it's your turn to apply these skills. Drop a comment below and let me know what you're building. If this helped, smash that like button, subscribe to BK'sTechStack for more weekly tutorials, and share this with someone who needs it. Visit www.BK'sTechStack.com for free resources, exclusive tips, and our community. Next video, we're diving deeper. Don't miss it.